because wastewater by nature is odorous, right? It can give out a very bad smell. And I don't need to tell you this, but odor control, there are a lot of sources from homes, from industries, and all of these have certain compounds which can release offensive smells. And that's why odor control became important. So as an example, if you take New York State, they have a very, very strict odor requirement where they say that there should be no emission in air, which interferes with the enjoyment of life. Like as humans, you can think about it. If there is an offensive smell somewhere, would you like to stand in that place, right? That's what it is, that you don't want any offensive smell where people are complaining, because it's not just about people complaining. Think about a neighborhood which just smells bad. No one will want to buy a house there. No one will want to visit that place, right? The overall property value of your homes go down just because of those odors being released from the wastewater treatment facility. And if you look at odor control broadly just for a minute, we are not just limited to wastewater treatment facilities which are in neighborhood. Think about a bakery, think about a restaurant, think about a meat shop or a meat rendering facility. All of these kind of places tend to create their own unique odors, and they are right next to homes or neighborhoods. So if you have some really offensive odor, you will not like it and you will complain about it, right? And you will go and talk to the owner of the restaurant, or you'll make a complaint to the municipality that, hey, listen, there's a bad offensive smell here. So think about it this way, that wastewater treatment facilities are going to produce a lot of odors, and they have to be very careful. Otherwise, public complaint can be a big problem for them, not only from a regulatory standpoint, but also think about the plant's reputation and everything. And no one wants that. So that is why odor control is crucial, because people are involved. However, odor control has evolved quite a bit. And the more science and the more research has been applied to odor control, ultimately more than just public health and comfort and regulatory compliance, it has also come down to the very workers who are exposed to these odors in wastewater treatment facilities. Now, the most common odor typically in wastewater treatment facilities is hydrogen sulfide gas. And this gas is not only toxic for humans, but is also very corrosive in nature, because in nature, in the presence of water, hydrogen sulfide gas can convert into sulfuric acid and cause major corrosion. So now you see that why odor control is becoming very important, whether it's from a communication standpoint, whether it's from a plant personal standpoint, whether it's from a regulatory standpoint, or even if you are a design engineer or a wastewater practitioner who is trying to design a system, why odor controls considerations are necessary. Okay. So let's take an example. As I mentioned earlier, that H2S is by far one of the most dominant gases in odor treatment. However, there are other different kinds of gases which will be released, so which we will be seeing in a few more slides. But just taking the example of hydrogen sulfide gas and how toxic it is, you can see on your screen what happens when you're exposed to different concentrations of H2S gas. Now, Occupational Safety and Health Administration states that if you are exposed to an environment of 1 ppm of H2S, you cannot work more than 8 hours. And STL, which you see at the bottom of your screen, stands for short-term exposure limit, which is 5 ppm. So if you have a short-term exposure limit is basically 15 minutes or under, you cannot be exposed to more than 5 ppm of H2S concentration. And higher the concentration you get exposed to, the more hazardous and dangerous this gas gets. So you can see why 90%. Hello?
I'm sorry for the interruption. Are you changing the slides?
Yes, we are.
Unfortunately, I'm not seeing.
Oh,
yeah, it's
sorry,
been like in the first slide since we started the presentation.
Yeah.
Oh, I'm really sorry. Can you see it now?
Yeah, now we can see, I think.
Maybe can you
Lars,
do the projection mode?
Yeah, the projection mode.
Yeah, I did the projection mode. I did
Actually,
that.
Can you press the F5? I think it should present just like that.
Yeah, I did that actually. I'm really sorry, guys. You should have just called that earlier. Can you see my screen now if I'm moving this one? I think it has something to do with my computer.
I think, are you using two screens
I
together?
have 4 screens.
Four.
Yeah.
Okay, maybe I think you selected the wrong screen for, like,
Okay, 1 second. Let me see what I can do here. I'm so sorry. So, I mean, just quickly recapping all of this stuff we have just talked about. As I was mentioning, did you get to see this slide?
No, we're stuck in the first one.
Oh, I'm really sorry. Okay. I already went to the fourth slide. My bad. 1 second. Let's see again if this works. Okay. Are the slides moving now?
No.
Nope.
Yeah.
Okay. That's interesting.
I can see different slides though. They're not moving individually, but I mean, I'm seeing this slide and then that slide and then another slide.
Yeah, I mean, we can go through this way, but
Okay. Okay. I guess we'll just have to do it this way then. I'm sorry. I put it on my largest screen. This is my television. So probably that could be the reason.
yeah, somewhere in this, I think slide 4. Yeah.
Yeah. Okay. You guys can see this, right? Is this visible to your screen? So I'll
Yeah.
just do it this way.
Yeah.
Okay. All right. Sorry about this. So, as just to recap quickly what we spoke about, as I mentioned, there is a lot of regulatory language to this, right? So if you think about it, you have to not only neutralize odors, but you have to maintain worker safety. So Amit, you are an operator, so you understand the importance of odor control, right? That plant personnel should take utmost precaution when they're getting exposed to odors. And then, of course, the whole purpose of odor control in your plant is because you want to make sure there is no H2S getting released into the atmosphere, which can cause corrosion to your infrastructure. One point probably I would like to add here is I'm not sure if any one of you has heard of this term called asset performance management or asset management. So a wastewater treatment facility, any equipment or any system you have within the plant is an asset. And you want to get the maximum value out of it because you have spent a certain amount of money on it, right? However, if there is excessive amount of corrosion and your equipment is getting damaged, you need to maintain it a lot. And at the same time, you're not getting the full potential out of it. So that is also another step. So Rebecca, as you are a communications personnel, asset management is also a big area. It's mostly project management and technical, but also getting the maximum value out of your plant is absolutely necessary because ultimately these facilities are running on tax dollars, right? So you want to make sure that you are reducing your operation cost, not increasing it. So that is also one reason why odor control is very important. Now, this was the slide I was on. And as I was mentioning to you guys that H2S, hydrogen sulfide gas, by far is the most hazardous gas and the most predominant gas in odor control for wastewater treatment facilities. However, as you get exposed to higher concentrations, it can be very dangerous for humans, right? So everything clear till here? Could you guys give me a thumbs up?
Yes.
Okay.
Are you
Okay.
going to the slide 2 with us?
Yes, we will share the slides with you guys. Okay. Now, coming back to the point of asset management, which I mentioned to you, just taking the example of United States alone, we are looking at just corrosion. I'm not talking about odor control corrosion. I'm just talking about corrosion in general, costs about $36 billion. And odor control typically in wastewater treatment facilities is in the form of a new term called MIC, which is microbial induced corrosion, which is basically, again, H2S gas, which is getting released, getting converted to sulfuric acid, and then causing corrosion. So if you just had to take the example of United States, I'm not talking even globally, you're looking at 10 to 20% of this total $36 billion per year coming just because of odor control or MIC, because of microbial activity, which is causing corrosion. So that's still a big value. That's like $3.6 billion to $7.2 billion worth of corrosion being caused just because of odor control or because of the conditions we are creating in our infrastructure, which is leading to corrosion, right? So this is how important odor control is becoming, that it's not just about the people anymore. It is also about making sure you can preserve your assets and your plant performance and everything. So as an example, let's just take your wastewater treatment facility, okay? You have different places where you are going to be producing odors, but just taking the example of H2S gas, again, as I mentioned, there are many different kinds of gases out there or contaminants. We are focusing on H2S right now because most of the treatment technologies predominantly have been focused on H2S. And you saw the reason why. One, because of worker safety, and two, because of saving your assets and everything. So this is just a general idea of what I have seen typically working at different wastewater treatment facilities coast to coast all over North America. Depending on the conditions and how old the infrastructure is, you can create very high concentrations of H2S as well. And workers can get exposed to it. So neutralizing H2S in these equipment or areas of wastewater treatment facility becomes very important. So till now, we discussed about overview of odor control. We also looked at where you could find H2S. Of course, there are some other contaminants which we will be touching upon in a few more slides. But now let's talk about how odors are formed. It's important to know what is the source of odor. And as I mentioned earlier when we started, it's a biochemical process, but you will be creating odors almost always in anaerobic conditions, no matter what. It cannot be aerobic conditions, it cannot be anoxic conditions. So for those of you who don't know aerobic and anoxic conditions is when you have plenty of dissolved oxygen in your water. And then anoxic condition is where you don't have free oxygen, but you still have something like a nitrate, like a combined oxygen. So this will help prevent odor formation. Anaerobic condition is when your water starts having no dissolved oxygen, and that's when microorganisms start reducing conditions within the water, which can lead to odor formation. So this is very important to remember. If you have aerobic or anoxic conditions, you will never produce odors. Now, how strong is your odor going to be? That's the next question. Now, in winter months, typically, biological activity is reduced. You know, microorganisms or bacteria are just like us humans. So they operate and function better in warmer temperatures. And typically, if you increase the temperature by 10 degrees Celsius, you double the activity of your microorganisms. So warmer the temperature, the more odor control forming potential. So take the example of states like Texas or Alabama or Florida, where throughout the year you typically have very warm conditions. That can lead to the formation of more odors, H2S, VOCs, ammonia, among other things. Low dissolved oxygen or no dissolved oxygen is already spoken about. We said that it's anaerobic conditions, so you will not have any oxygen, which will lead to odor control formation. High BOD and COD loading. So Amit, you're a plant operator, so you would know the meaning of this. But for those of you who don't understand this, our body or whatever discharges we have in wastewater tends to have a lot of organics, which we measure in the form of BOD, which is biological oxygen demand or chemical oxygen demand. So the more organics which are present in the wastewater and the more anaerobic conditions we have the tendency to create higher concentrations and more odors. The next thing is sludge age and retention time. So if your wastewater is not moving fast enough in your distribution system, or it's not getting transported fast, or it's not getting treated fast, what's going to happen is it stagnates. And when it stagnates, you will again create anaerobic conditions, which can lead to the formation of odor. Now, it's important to understand this. you must have learned in school laminar condition and turbulent condition. In laminar condition, you will have odor formation, but you won't see it that uniquely. And part of the reason is why, because in laminar flow, the gases are still dissolved in the water. But the moment you create turbulent conditions, which is vigorous mixing or transportation of the fluid, you will see that these gases start leaving the water. And that's when you get more smell. So whenever wastewater is moving, you tend to get more odors compared to when water is not moving. Okay. Now, this is just a general guideline, what you see on your screen, as to where odors are going to be formed in wastewater. Now, this is a tip for all of you. If you ever become odor control practitioners, is how do you know what is the odor causing potential of your wastewater? What you can do is, these days you have these ORP handheld probes. You can simply insert them into water. And once you get a result in negative value, you can know that, okay, this water may have a chance to produce odors. But if that value is positive, that means that you may not produce odors. Now, for those of you who don't understand ORP in a non-scientific way, let's just put it this way. It's called oxidation reduction potential. However, ORP in layman terms means the cleaning power of water. So higher the value or more positive the value the ORP is, that means that there are enough oxidants in the water that water can clean itself. The more negative it is, means that the more oxidants or dissolved oxygen you need to add into the water so the water can clean itself. Okay? So this is what it comes down to. Whenever the conditions are negative, it is going to be anaerobic condition and you are going to produce odors. And these are just some guidelines as to what you can follow. Now, this is something, Amit, I think you will really understand. And for those of you, we will explain this again, how odors are formed and how they can lead to corrosion. So what you see on your screen are typically a rising main sewer, which is also called a forced main. This is basically a pipe which conveys wastewater at an elevation. And then we have something known as a gravity sewer. A gravity sewer is nothing but, again, a place how you can transport wastewater, but instead of using a pump, you use gravity. So you are just using nature to make sure you can transport your wastewater. So let's show you an example here. What you see on your screen is an equation, just a general equation again, where you have organics, you can have nutrients, and because you need anaerobic conditions to create odors, you no longer have oxygen. And for microorganisms to thrive, they need some food. Of course, they are getting the nutrients and the organics, but they also need an electron acceptor. So because oxygen is not available, you will be using sulfur or sulfate, more specifically, as your electron acceptor, which will help with the conversion of these organics to sludge, but also lead to the formation of odors. So in this diagram, say you have a pump station which is pushing the wastewater, and over time, you create anaerobic conditions. Now, when microorganisms grow, for those of you who have not dealt with wastewater before, microorganisms, when they grow, they tend to release a sticky substance called EPS, extrapolymeric substances, and these are very gluey materials which tend to stick on the walls of a sewer. So when anaerobic conditions are developing, this will lead to the formation of H2S gas, as well as some of this H2S gas is going to be ionized, as you can see on your screen from the equation. So you develop the anaerobic conditions, and there comes a time when it is getting released near a manhole. That's when you will notice some odors. So whenever you go in a city and you stand in front of a manhole, you'll smell something odd, right? That is what is odor control. That is the odors which are being formed from the wastewater, because typically these sewer pipes tend to be beneath us, below roads. So if you're going by a manhole and if you smell, especially in winter months in Canada, if you get very offensive smells, 99% of the time, it could be some cause, some form of odor, which is just coming out. So this is how odors are getting formed in manholes and sewers within Canada, or be it anywhere in the world for that matter. The science is going to remain the same. This is just a general demonstration of how odors are getting formed and how we can get an idea of what could be the reason for this odor formation. Now, when we expose this anaerobic water to, say, an atmospheric condition where there is oxygen, some of these odors are going to get released. However, some of these odors, in the presence of oxygen, water, and H2S, will convert that H2S into sulfuric acid, which I mentioned to you. And again, because of these extra polymeric substances which are being released by microorganisms, they tend to stick on the pipes of your sewer or on the walls of your sewer, and hence you can have corrosion formation. So all the things we just discussed about, this is a more practical way of showing it to you guys that how odors are not only being created, but they're also simultaneously causing corrosion. I hope everything is clear till now. You're more than welcome to stop me and ask me questions. Amit, Rebecca, Hajara, Afrida, I know it's only 4 of you, so I'll be more than happy to take any questions at this point.
I think we're good. I'm good.
Okay, Rebecca, I hope, I know there's a little more technical, but if you have any questions, just if you want me to explain it in a little more non-scientific terms, please let me know.
Thank you. It's shockingly straightforward. I'm grateful.
Okay, all right, well, we'll get moving on then. So, as I mentioned, most of the times H2S is the most predominant gas in wastewater treatment. However, microbial reactions are very, very, very complex, okay? And ultimately, it depends on what we are dumping into our wastewater, whether it's from homes or industries or whatever it is. The makeup of your wastewater can be very different. You can have a lot of nutrients, you can have a lot of sulfurous compounds. So in odor control, you're not just limited to H2S. I think this is one of the biggest challenges I see as a practitioner, is explaining to people that it's not just H2S you're targeting. There can be a ton of other compounds which can be hazardous. So as an example, what you see on your screen with organics, you can have reduced sulfur compounds. Sulfur is an inorganic, as we know, we all studied in school, but it can also combine in organic form, and it's called reduced sulfur compounds or mercaptans. They also tend to have a specific kind of odor. Then you can have industrial discharges where you can have toluene, benzene, which can also have a lot of different kinds of odors. I do see 2 questions, Afrida and Amit.
So yeah, when you said in the inorganic side, you will be getting the H2S and the organics. What is the maximum concentration that you can see for toluene and benzene? Because I think these are all carcinogenic, right? So
yeah, they're carcinogenic. You can see 1 to 2 ppm. It really depends on the source, right? Most of the times, from my experience, at least everywhere I have been, I have seen ppb level concentration, so it's not that bad. But sometimes you can have ppm level as well. It really comes down to the composition of your wastewater, right? Is it more homes? Is it more industrial wastewater we are dealing with? So it comes down to a lot of that as well.
So when it comes to dealing with the municipal or industrial, do you see more in the industrial side or the municipal side?
More industrial side, I would say. More industrial side, absolutely. But sometimes you can have, depending on how much industrial wastewater is making up, a wastewater treatment facility's composition, you can see elevated concentrations, but not a whole lot. It's mostly industrial wastewater if you go to petrochemical facilities and everything. But when dealing with municipal drinking water or wastewater, sorry, you can see some mercaptans, H2S and ammonia more predominantly.
Yeah, that's true. Okay.
Yeah. And Afrida, you had a question? Okay, all right. Now you can also have some nitrogen-based compounds. So we all love eating a lot of meat, right? And when we discharge or excrete all of that eaten meat, it's in the form of protein, right? We use some of it, we release some of it. And proteins can also be broken down by microorganisms and can lead to the formation of nitrogenous compounds. Yes, Amit.
Are you still in the slide 11 or?
I'm in slide 11.
Oh, okay. Sorry. Never mind.
Yeah.
Sorry.
Yeah, I'll keep changing, so don't worry about that. And lastly, I would like to also point out chlorine gas and chlorine dioxide gas are typically very common disinfectants used in wastewater treatment facility or drinking water facilities. That's like the final step before the water is discharged. So sometimes what happens is if your storage tanks fail, you can end up releasing chlorine or chlorine dioxide gases, which can be hazardous. And you need some kind of emergency scrubbers. So to make sure that none of this chlorine gas is toxic to workers and everything. So you can see that there are a wide range of compounds, not just H2S, which can be released in odor control. Now, what is interesting to note is every compound on its own has a unique smell. Hydrogen sulfide gas, Rotanex smell is very, very common. But if you go to a reduced sulfur compound like methyl mercaptan, as I showed you previously, it's an organic sulfur compound. It can have a rotten cabbage smell. If you go to BTEXs, you'll get a very sweet aromatic smell, very similar to what fragrances are like. Amines can have a very fishy smell. And you can have also alcohols or even acetone. Most of you know nail polishers. Pretty much everyone would have used it at some point. So that distinct smell you get is because of acetone, right? So you can see that every contaminant has its own unique smell. And this is not a comprehensive list, but most of the times these are the kind of compounds we have seen in wastewater odor control treatment. So that's why I wanted to present this on the screen. Now, what can be confusing though, and Amit, I'll get to you in a second. What can be confusing is, suppose if you have a mixture of these compounds, it can get very confusing for humans to know what could be the main compound which is causing that odor. So that's why analytical testing becomes very important. Amit, go ahead.
Sorry, that was by mistake. Sorry.
Okay, that's fine. So as I would like to repeat, when you're getting a smell and you say that, okay, you know, I'm getting a Rotanex smell, it could be H2S, I always still recommend that get a full analytical test done. And part of the reason is because sometimes human can get confused. Every human is different. Their sense of smell is different, right? So that's why it's very important that unless you're absolutely sure, it is always better to do some analytical tests to know the composition of your air rather than making an assumption that, okay, this smell would probably be related to a certain compound. And why do I say this? Now, this was just general science for human perception of smell. Because every compound has a certain human detection threshold. So as an example, I would like to point out ammonia here. Only at 17 parts per million or 17,000 parts per billion is ammonia noticeable. However, I have had the opportunity to stand in ammonia in air environments. And I have noticed that even at a 5 to 10 ppm concentration, it gets very annoying. Even though I'm not able to smell ammonia, it is still very irritating to be around ammonia, even though it is less than 17 ppm. Now, ammonia is not hazardous at 5 to 10 ppm, but it can cause some irritation. However, only when you get to 17 ppm or 17,000 parts per billion is when you can get that unique or unique ammonia smell, which based on the previous slide, if you refer back, ammonia is going to have a very sweet urinary smell, right? So that's why it's very important to do an analytical test, which is the next thing we are going to be getting into. And hydrogen sulfide gas, it is very a unique smell, again, Rotanex smell, but even at 0.5 parts per billion, just very minute concentration, you can get a Rotanex smell. But again, depending on the compound, that threshold or concentration can change. Now, just because some of these have a very high concentration does not mean it's safe. You want to make sure you are not exposed to these kind of odors for a very long time. Yes, Rebecca.
I'm just wondering if you can put the names of the chemicals to something a little bit more familiar for us. Like, for example, things that you might encounter, urine or food waste in the sewer, which chemicals would be associated with?
Okay, so in wastewater treatment, like these are the smells, right? So like I mentioned, every compound has its own unique smell, okay? However, when you have a mixture, right, it gets very confusing. So that's one thing, but you were wanting to know about this slide, like what smell is associated. I was not able to understand the question fully.
If it's appropriate, do these chemicals come from anything in particular? Like, for example, what would ammonia be from? Like,
ammonia is from humans.
The presence
ammonia,
of something.
Yeah, so ammonia comes from humans, and most of these compounds, what I'm showing on the screen, more or less are formed because of wastewater itself. Like as I mentioned at the very start, wastewater can have different kinds of waste, right? It's typically organics, and it's very complex. You can't just pinpoint to one biological reaction that okay, you are going to produce only a certain compound, right? It's very complex. Microbial activity is very complex, and it's typically human excretion as well as industrial discharges, which leads to this. So I would say H2S is very understandable, and part of the reason is you can read more about it. I can give you some more literature, but just going back to this one equation here, as I mentioned at the bottom, C is carbon, H is hydrogen, O is oxygen, N is nitrogen, P is phosphorus, S is sulfur, right? So these, there could be a big different makeup of your organics or your nutrients, which are coming into the wastewater. But ultimately, the microorganisms are using the sulfate, and they're breaking down this big organic chain right here, which is leading to different kinds of odors which are being formed. So what you see on your screen here, you can form ammonia, which is in ionized form. You can have phosphate, you can have H2S gas, and here this is called methanol. So this is just a very general example. There are a lot more equations, but again, I'm not a biochemist, so or a microbiologist. So to understand each and every odor formation and its path of which compound is being formed, there are multiple reactions. So it's a very complex biological reaction. I hope that answers your question to some extent.
Yes, thank you.
Okay, so we have just about another 30 minutes. Now that you guys have understood why is odor control important, how are odors formed, and what can be some distinct smells of compounds causing odors, let's look at how we can measure odors. So the interesting thing about odors itself is the science has not been well understood. There is still a lot of work going on. And part of the reason is because we as humans can smell at least 10,000 different kinds of smells. And the other problem is that whenever we smell an odor, right, we try to associate it emotionally to something. So that's why scientists have still not been able to figure out why is it that we have an emotional reaction when we smell odors. The interesting thing though is women tend to be better at smelling odors than men. It's actually a fact. Women are best in everything compared to men. But this has also been proven scientifically that women are better at detecting odors than men. So the general mindset always with odor control was, if you see previously, that if I can smell something, I'm definitely sure this is an odor. However, how do we make it very scientific, right? That's where olfactometry, a science, comes into play, which basically is measuring odors and telling you the intensity of odors. Now, note, this is just one way of measuring odors. It's not telling you exactly what is your source of odor or what kind of compound is responsible for this odor. It's just telling you that there is an odor and there is a certain intensity to it. Okay. So, in a lot of municipal projects or in regulatory compliance, there is a term called odor units, which is very commonly used. And to do this kind of test scientifically, you have a couple of people and you introduce a certain amount of odorous air and you dilute it with fresh air. And you want to make sure that 50% of the population, which is sitting at an odor panel, is able to detect the smell. And that is what is known as odor units per metric cube, which basically means that 50% of the population is able to detect an odor. Now, this is a very crude way because every human, as I mentioned, has a unique sense of smell, right? And for that very reason, this test is just going to tell you about the intensity of the odor, but again, it can be distinct and every person can have a different perception. One other thing to notice is one odor unit per metric cube. Suppose if you had to quantify this, one odor unit per metric cube means that there is an odor, there is a smell. But as this number starts getting bigger, say 5 odor units per metric cube or 10 odor units per metric cube or 100 odors per metric cube, your odor intensity is increasing, means the air is getting more odorous, right? So this is how you quantify an odor stream and its intensity. So in a lot of these municipal bids or regulatory compliances, just take an example, City of Toronto, they say that no facility should be emitting more than 1 odor unit per metric cube of odors, right? It doesn't care about what source it is. It does not care about what would have caused it. It is just telling you that the intensity of odor from this facility should never be more than 1 odor unit per metric cube, okay? The interesting part though is, as I mentioned about H2S gas earlier, imagine if you had 100 ppm of H2S gas and you had to tell your odor panelists to get exposed to this 100 ppm H2S gas. It could be dangerous and life-threatening, right? And that's where, if you wanted to scientifically measure how much odor units per metric cube are coming from a certain contaminant, let's just take an example of ammonia, because you all must have seen when I was on the slide that 17,000 parts per billion is when you can detect ammonia. So the equation which is given here, for example, your actual concentration was 34,000 ppbs, and your threshold concentration for detecting ammonia is 17,000. That tells you that your odor units per metric cube, it calculates to 2. So it's telling you, based on the scale, that yes, there is an odor. We know that it's from ammonia, but that is the intensity of this odor. So if ammonia concentrations were higher, that odor unit per metric cube number is going to keep rising up. Okay? Is everything clear till now? Because odor units is a very, very funny thing. A lot of people get confused. So I just wanted to know that. Yes, Amit, go ahead.
So you said that the odor unit is actual concentration divided by your threshold concentration, right?
That's correct.
So for that threshold, is that the limit that you're sharing with us? Like 17,000 for ammonia and those numbers?
Yeah.
Okay, so that ratio should be like just 1.
It should be 1 or under. Typically, in some places where the facility is very near to the neighborhood, they say that less than one, because one odor unit per metric cube is when the odor is just detectable, right? As I mentioned, 50% of the people should say that there is odor. 50%, if they don't agree there is an odor, that's okay. But at least 50% of the people should say that, yes, there is some kind of noticeable odor. So that becomes one odor unit per metric cube. However, again, as I have been telling from the start, that suppose you had 20 people, 10 say that there is an odor, 10 say there is no odor. That is still considered one odor unit per metric cube. However, if only one person detected odor and 19 said, you know what, we don't smell any odors, then there is no odor problem, right? So again, I don't really like this method. I know it has been developed and it's being used, but there is no real way to quantify this, right? You're just getting to know about the intensity from a human perspective. But that's where analytical testing becomes more important, which we will be covering in later slides. Yes, Afrida.
Okay, so I want to ask you, like, how can we build the trust when not everyone senses things the same way?
And I think that's exactly where I was going to talk about the other slides. I personally, what has happened is over the years, right, every facility tends to produce a certain kind of odor. Like in wastewater treatment facilities, it's mostly H2S. If you go to a meat rendering facility or meat shop, it typically is organics or ammonia. So people have, of course, done a lot of work to know that, okay, what could be that contaminant which is causing that odor? But for public, they don't care about H2S or ammonia. They just care about odor, right? They are just concerned about, okay, you know what? I'm getting a smell. If I'm going to be exposed for it for a long time, this is offensive for me. So odor units was developed for the public in such a way that, okay, if anything is over one odor unit per metric cube, it's going to be bad. And long-term exposure is just not good. I'm not going to be able to enjoy this environment, and I need to get away from this environment, right? That's all really it is. So as much as people try to say it's scientific, I'm not such a big fan of it yet, but it is actually something which is used on a regulatory basis. Now, one very good example I can give you, I moved to Canada in 2018, and cannabis became a very, very big thing. Like, it was legalized and you could grow cannabis and everything. And cannabis tends to have a very, very strong odor. And most of these facilities are near neighborhoods or farms, right? So people had to figure out a way to treat these cannabis odors because they are very offensive in nature. So there was a big push for using nasal ranger, which I'm going to be showing you in the next slide, actually, which helps measure the intensity of the odor. So most of the times, there is what regulations are set by government is that, okay, at the fence or at your boundary, you can have one odor unit per metric cube, but that's it. Anything above that, you are going to have some kind of fines or something. Okay. So I hope that helps answer your question to some extent.
Yes, thank you.
Okay. So now we have just understood a very basic way of measuring odors, right? It is just telling you an intensity, and when humans smell it, they can tell that, okay, there is odor, there is no odor. And then a more scientific way, if you had a certain contaminant you already knew about, you wanted to measure it, but do not want to expose your human panelists to an odor panel because of safety reasons, you can calculate it by using this equation. But scientifically, I would say that there are better ways to do it, right? You have portable instruments these days. These can be, there are many out there in the market, but these are meant to measure individual gases. So, for example, what you see on your screen, on your left side in the yellow, it's called a multi-ray. This is a multi-gas detector. So you can do H2S, ammonia, and VOCs in one go, but it is going to just measure your odors at that specific time. So the thing about portable units is you can move them around and you can measure the concentration of certain contaminants at different areas of your facility. The one you see in the center of your screen is called the nasal ranger. This is typically used for odor intensity again, something we just talked about in the previous slide. It is just going to tell you about how offensive this odor is. So the guy holds the machine on his nose. Believe me, you need very strong lungs to even run this unit. He will keep changing the dial to measure the intensity of the odors and everything. And then you have some other instruments which can be used. But again, there are limitations with portable instruments. If I'm in a wastewater treatment facility, 90% of the time, I know it's going to be H2S, ammonia, or VOCs. So I will just go with one of these handheld analyzers, and that at least helps me get enough data and information. But what if I had to go to any other facility? I will need to get a portable instrument which is specifically designed for that specific odor, right? So that's where portable instruments have certain limitations, that it is good for H2S, ammonia, and not a qualitative data of VOC, but a quantitative data of VOC. So at least you get an idea. No, Afrida, no, they will not be able to distinguish between different odorous compounds. They just tell you a concentration, right? And there is a way to do that as well. I'm going to show you the lab technique on that. The other thing about portable instrument devices is they can run for about 30 days continuously. So if you wanted to get good comprehensive data for your facility, you can place it at a certain point where you want the measurement, and it can give you a graphical or Excel representation of the concentration over a time period up to 30 days, and you can always output them. So that is very good for portable. They're quick, easy, cheap. Use them, they're mobile, you can take them around. Now, there are some facilities, like wastewater treatment facilities, who are really concerned about how much odor could get released, or petrochemical facilities, biogas facilities, oil and gas facilities who are really worried. They can use something known as an online analyzer. So it's basically an instrument which is connected to your airstream, and it is continuously measuring the H2S or any concentration or specific gas you're looking for, and it's giving you an output continuously. So these are typically $50,000 or above instruments, and they need to be maintained, and they kind of give you an idea of how much H2S or other kind of contaminants you're producing continuously. Now, these tend to be very expensive. Sometimes, depending on the facility, you can get away with portable instruments, but some facilities have it as a must because, again, there are certain kinds of compounds which can be explosive in nature, right? So you have to be very careful. And for that reason, especially in petrochemical facilities or oil and gas facilities, if they have to take care of odors, they make sure to have these analyzers so they know that they are meeting permits, but they're also not creating any explosive environments. Now, to answer your question, Afrida, how to know whether we have a wide range of compounds, right? Sometimes, and as I have mentioned, portable instruments work excellent, or even online analyzers work instrument. But what if you wanted to understand the whole profile of exactly what is the buildup of, what is the odor buildup of your air, or what are the different kinds of compounds present? That's where lab testing comes into play. So you have something like a simple pump, you connect to your odor stream or airstream, and then you take out a portion of your air and you send it to the lab. The lab will analyze it using gas chromatography or mass spectrometry and will give you a concentration of all these compounds. So I'm actually going to be showing you this after we are done with this presentation. I'm going to be showing you what a lab analysis looks like and how it breaks down different kinds of compounds and everything. So these are very straightforward setup. What you need is tubing. You need a flow controller, all typically provided by the lab. You connect it to your airstream. You collect the sample and give it to the lab the same day, and they can analyze the odors for you and give you the breakdown of every compound or contaminant which is present in your air. Okay. The last thing in measuring odors is dispersion modeling. Now, this is more done to make sure how far your odors are going to spread. So as an example, you are trying to build a new wastewater treatment facility, or if you are trying to expand your wastewater treatment facility, and you wanted to understand the impact of odor spreading into a neighborhood and the intensity of it, that's where you do dispersion modeling. So it's a software where you will be inputting your source of emission. You will be, inputting what is your wind speed. In Canada, we tend to have really fast winds. So especially in summer months, you can have air spreading much faster. You can have terrain conditions. So, you want to input your geographic conditions. And all of this will give you an output and tell you what you see on your screen is an example of how far these odors are going to spread. So red means it is very intense, and purple means that the impact of odor spreading is going to be very limited. So that's why doing this is important, because as I have been telling from the start, there is a big regulatory compliance, there is your plant's reputation, there is safety of people, there is asset management. All of these things have to be considered. And that actually helps a lot of these facilities make a decision whether they need some kind of neutralization for your odors or not. Okay, so this was the second segment of this presentation. We have now looked at how odors can be tested for and how we can quantify them. So now I'm open to taking any questions before we move on to treatment technologies. Any questions? Okay. Thank
So
you. Yes, Amit.
So the modeling, normally you do the 2D dispersion?
You can do 2D or 3D, but 2D is more common. Yeah, because the funny part is we don't have a very specific odor control dispersion modeling software. These AeroMods and CalPlus softwares were developed by EPA, and these are like around 20, 30 years old. So they have been used for petrochemical facilities or any other facility which produces any kind of gas which can be hazardous, right? So odor control, because H2S being a corrosive gas, can also be modeled. So that's why you have dispersion modeling. So mostly dispersion modeling has been used in petrochemical facilities or biogas facilities and everything, because there you can have much higher concentration of contaminants. Not so much with odor control, except a few facilities, but it's always good to do it because, again, it's people are involved and safety of people is very important, right? So, for example, I have seen this a lot in York region in Ontario, which is north of us. They do a lot of dispersion modeling because they have at least 20 plus facilities which use odor control. So, and they're near neighborhoods. So understanding how far the odors are spreading is very important for them. So they don't have to deal with any compliance issues. I hope that answers your question.
Yeah, okay. So you said there's this AeroMod?
AeroMod.
Okay.
Yeah.
I think we can do it in the MATLAB also, right? Just inputting the numbers like the source of emission, rate
Yes,
of...
you can do that. And I mean, individual, the thing is individual, how should I put it? There are some odor control companies which have developed their own software where you can input the geographical conditions or latitude and longitude. You can, at a specific time, measure input wind speeds and everything. And that will kind of give you how far the odors are going to go, right? So there is one company you can check out. It's called Sencroy. I can put it in the chat box before we are done here today. So you can go and check out. They have a very simple Google cloud-based software where you just go, input all the values, and it can give you a dispersion model, a basic dispersion model of how far the odors are going to spread. You don't need to do it too mathematically because there are a lot of inputs typically involved in these kind of softwares. It's just like, if any one of you attended wastewater modeling, right? There are a lot of parameters to look into. Same thing happens in dispersion modeling. You have a lot of parameters you have to input to make sure you get an exact idea of how, in how much time will odors spread and everything. So That's why I sometimes say that it's always better to just have a treatment unit than just spend time in dispersion modeling. And part of the reason is because dispersion modeling can get very expensive. And if not done properly, you can have very wrong results.
Okay. Yeah.
All right. So the last step we are going to do is treatment technologies. This is my bread and butter. That's what I do on an everyday basis, actually. Utilizing odors and having equipment, doing startup and commissioning of these systems is something I have done coast to coast all over North America. And typically, we have many different kinds of ways odors can be treated. Now, you have to understand this. I showed you an example earlier of forced main sewers and gravity sewers. That is what is called a distribution line treatment of odors. You end up using technologies like ionization or chemical treatment. You end up adding calcium nitrate or hydrogen peroxide or ozone. Again, all of the conditions are anaerobic, and by adding these chemicals or gases, you are trying to create aerobic or anoxic conditions so that odors can be suppressed, their formation can be suppressed. But when you get into a facility, and not just wastewater treatment, but when you look at oil and gas facilities, or if you look at biogas facilities, three most dominant technologies are activated carbon, chemical scrubbing, and biological treatment. And I'm not going to get into too technical design details, but at a high level, for everyone for here to understand, I will be talking about a few parameters and explaining why they're important. Now, the next question comes up is, what is the best treatment technology to use, right? Amit, you're a plant operator, and you will kind of agree with me that you have odors, you need some kind of an equipment which is very cost effective. You know, you don't want to spend too much money. Like the capital cost is high, the operational cost is high. You don't want to spend money on that technology. You want something when once it's set up, it's commissioned, it is working on its own, it is doing what it's supposed to do with the least amount of maintenance, right? Again, everything is an asset at the end of the day, and you want to get the maximum value out of any treatment technology by putting the least amount of time and effort and money into it, right? That is what that comes down to two very important things when you're trying to select the best treatment technology for your facility. The first is, of course, what kind of flow rate are we dealing with? Are we dealing with small flow rates, or are we dealing with very large flow rates? The second thing comes down to what kind of concentration and target compounds are we going to be neutralizing? 90% of the time it's H2S, but sometimes you can have ammonia, VOCs, BTEXs, among other things. So it becomes very important that you look at which treatment technology is going to be the best. There have been many cases at times where you have to combine two technologies just to get the best treatment. Many a times activated carbon system is used for small flow rates, but it can be used for large flow rates as well, depending on the concentration. But activated carbon is also used as a polisher. So if you're doing chemical treatment or biological treatment, which tend to be more expensive technologies, you tend to add activated carbon at the back end or downstream of these treatment units as a final polisher to make sure that you have no odors which are being released into the atmosphere, but are also meeting that 1 odor unit per metric cube criteria set by many municipalities. Okay, I hope everything is clear on this slide. Any questions, anyone? Okay, so I'll move on. Now, there are certain design terminologies you need to know, right? And part of the reason is because these are terminologies you will be using across all the different kinds of treatment technologies. So the first one is concentration, right? I mentioned to you guys earlier concentrations in ppm or ppps. However, how do we quantify this? So for example, you had H2S because most of these technologies are designed for H2S removal, but I'll explain a little more as we get to each individual technology. Each technology can treat a certain amount of odors. But for example, if you had H2S, right, and you wanted to know how much H2S you're producing per day, now ppm is not a good number. You need to know how many pounds or milligrams of H2S you're producing, and that's where you have the units of micrograms per metric cube. So if you have been given a concentration in parts per million or parts per billion, you use this formula and you get micrograms per metric cube. And then you multiply this number by your flow rate, which can be in metric cubes per hour or cubic feet per minute. You just have to do basic conversions from SI units to imperial units. And then you multiply this number by 1440, which is basically the total number of minutes in a day. You get the total amount of a certain contaminant or H2S or ammonia, whatever it be, produced per day. And based on that, you can decide which kind of technology is better based on the flow rate and the concentration and the amount of contaminant you're producing, which technology will be the best one to use. The other thing interesting to know is we deal with a very small unit of pressure. So in most cases in water, wastewater treatment, we deal with PSI, pounds per square inch, very common unit to use, or we use kPa. But here we are using a much smaller unit called inches of water column. And 1 PSI, 1 pound per square inch is equal to 27 inches of water column pressure. Most of the treatment systems which are designed in odor control are designed for less than 20 inches of water column pressure. So the total pressure a system can handle is less than 20 inches of water column, which is less than even 0.75 PSI. Just to give you an idea of how crucial pressure drop can be. And why is this the case? Because we don't use any complex rotating equipment. We use only a simple fan. So for those of you who have not dealt with fan, it's a rotating equipment, just like a pump, just like a compressor. And its job is to move the air, because ultimately we want to make sure that we are able to move odorous air through the treatment equipment so that we can neutralize the odors. So that's the purpose of the fan. I hope everything is clear here. Okay. Moving on. The next thing is air changes per hour. So for example, you guys did not know volume of something, or you did not know how much flow rate is there to be treated, right? You can use air changes per hour to calculate how much flow rate you require for your treatment. So air changes per hour is pretty straightforward. It's basically telling you if you had a certain volume in a space, how many times will that volume of air within that space get displaced in an hour? So if it's 6, it means that, say you had 1,000 metric cubes of volume, 6 times in an hour, 1,000 metric cubes of air is going to be moved. And there's a very simple way to calculate this. This is typically used for pump stations, lift stations, where you don't know the exact volume, so you can calculate it. Yes, Amit.
So you just consider the standard volume of the room. You don't have to, and you consider that amount of air is being present over there.
Sorry, I didn't hear you. Can you repeat?
Is it like a retention time of the air in the room?
Yes. Yeah, so we are looking at the full volume, right? And as I mentioned, we are going to be using a fan. So that fan is going to help displace that volume of air quickly. So we take the entire volume of the room, everything, into consideration. And then we design a fan in such a way which can push that much volume of air continuously.
Okay.
Yeah. So this formula, what you see on your screen, you see CFM, that is your volumetric flow rate, right? That's the number we want to get to. The target range we have is 6 to 12, which basically means that the higher your air changes per hour, the bigger or larger the flow is going to be, so that you can keep displacing this air as fast as possible, right? So most of the times I have designed systems for 6 to 12 range, but in certain cases where the concentrations is very low, and they just want something as to just fine tune or polish the air, we have even used units of 3. which means you need a smaller system, because the bigger the air changes per hour gets, the bigger is your fan. That means that more pressure drop there is going to be, right? So you just want to make sure that you fine tune it in such a way that you can balance both your economic justification as well as your treatment justification. So calculating the right volume of the room is very important, and that will give you the right flow rate. And what you see on your screen here is for other places, like if you had a bakery, you had some municipal facility or restaurants or warehouses, they all have their own air changes per hour requirement because of safety reasons and everything. So fast food and bakery, they have much higher air changes per hour, and there's a reason for it, because if they allow the odors to stick for a very long time, well, your body will be smelling of odors, right? No one wants that. So this actually concept has come from the HVAC industry, which is where air changes per hour is a very common thing which is used. Okay. The two other things which are very important is empty bed contact time. So basically you have a big vessel, whether it could be activated carbon, chemical scrubber, or a biological treatment system. So there is a bed in there. Now this bed's job is to make sure you have a contact time. So what empty bed contact time essentially means is from the time the odor enters the reactor for neutralizing, how much time it spends in that bed, it gets neutralized, and then it gets discharged. It's as simple as that. Nothing too complicated. So what you do is you take the volume of your tank or your bed, and you divide it by the amount of air you want to flow through that reactor, and you will get a certain amount of contact time. So this is very crucial, because depending on the technology you end up using, this number will change. So as an example, if you're using activated carbon systems for neutralizing odors, you need only 3 to 4 seconds at max. But if you're dealing with biological treatment systems, you could need as much as 60 seconds of contact time. And the reason for this is because over the years with practice, it has been found out that these are the best numbers typically for neutralizing your odors, whether it's H2S, whether it's ammonia, whether it's VOCs. Okay. The next thing is bed velocity. In very simple way, it is basically how uniformly the air can be distributed in your treatment equipment or reactor so that you can get good treatment. Because if you had very high velocity going through your reactor, you will get a very short contact time. As you can see, more or less, both the equations are interconnected. So if you have very fast velocity through your reactor or treatment unit, that means you will have high pressure drop, which could mean that you may not get the effective treatment you're looking for. Too low, you may not move any air through your reactor. So you need to find a sweet spot for your bed velocity. And again, over the ages, there has been a range which has been proposed for various technologies. You typically want to be within that range. It is calculated in feet per minute. And bed velocity also plays a very crucial role, as much as empty bed contact time, in making sure how big of a system you need to design. I hope this 3 slides I covered till now on treatment technologies is clear to everyone, and the importance of it. Any questions? Okay. All right. So let's, I'm not going to get too technical now. We have a few more slides to go. I'll try to, I know we have I get very passionate about this subject actually, because that's my bread and butter, I would say. But let's get into activated carbon. It's a very simple process. Essentially, you have a carbon bed, typically 2 to 3 foot in bed depth. It's a very simple process. You have a fan, that is the only rotating equipment, and you evenly distribute the air, as we mentioned about empty bed contact time and bed velocity. This odorous air, or the air which needs to be treated, will pass through the carbon bed, and it gets the odors get neutralized, and then you have at the very top clean air which is being discharged into the atmosphere. If you look at it microscopically, for those of you, and I think Afrida, you mentioned that you have worked in drinking water. Amit, this is something you must have noticed as well. Activated carbon has a lot of nanoscopic pores, which are not visible to the human eye. So you need to use scanning electron microscope to see the surfaces. But essentially, you have different kinds of pores, which contaminants move through, and they adhere to the surface of activated carbon. So activated carbon in drinking water has always been used for organics removal, but by changing the surface chemistry or by modifying the surface of the activated carbon, you can use it for H2S, ammonia, and VOC removal as well. And again, when we deal with drinking water, we are typically dealing with only granular or powdered form of activated carbon. But when we get into odor control, specifically for treatment of air, whether it's in HVAC or even for wastewater treatment facilities, we can have over 20 plus recipes of activated carbon. So each carbon will have its own unique manufacturing process. You can have a virgin carbon, which is used for organics removal. You can have catalytic non-water regenerable and catalytic water regenerable carbons, which are specifically designed for H2S removal. You can have acid impregnated activated carbons. These are typically used to neutralize ammonia or amines from your odorous air streams. And then you can have base impregnated carbons, which could be something like a potassium hydroxide, a very commonly available chemical, or sodium hydroxide, which we all know, or even baking soda for that matter, which is impregnated onto the surface of the activated carbon, which can neutralize any acid gases. So H2S is an acid gas, and so is sulfur dioxide or any organic sulfur compound like mercaptans, which we discussed about earlier, which can be neutralized using activated carbon. I'm not going to spend too much time here, but basically, there are multiple flow patterns in which activated carbon systems can be configured. And again, it really just comes down to the amount of area or height available at a specific facility. And based on that, you can decide which is the best way or best technology to use. So you have a deep bed, which I just showed you at the very start. You can have a radial flow, and Amit at GE booth, as we were just discussing earlier, they are going to have radial flow activated carbon systems because they have a good height but a very small footprint. You can have sometimes, if you don't have enough height available, then you can use horizontal bed systems. And sometimes if you have a much larger flow, if you're dealing with, you can have something known as a V-bank, which is basically 2 horizontal beds. So I'm not going to spend a lot of time, but if you go on the internet and just look at the different configurations of activated carbon scrubbers, you can get understand more of this. We are kind of running out of time, and we still have 8 or 9 slides to go. So I just will try to speed up a little bit. The next thing is chemical scrubbing. A very simple treatment again. So what happens here is you have chemical which is being injected from the top, right here, as you can see. You have chemical which is going to be neutralizing your odors, which are injected from the top, and they're atomized. So if you have worked with a garden hose and you atomize your water, exactly the same concept. And the reason is because you want to increase surface area. So maximum amount of that chemical is used for neutralization. And then you have a packing bed. It is, as I mentioned, empty in the slide for empty bed contact time and bed velocity. You need to make sure that the odorous air is interacting in that packing with water or any chemical or activated carbon so that it can get neutralized. And then you have odorous air, or the air which needs to be treated, entering the reactor from the very bottom. And then you have clean air, which is released from the very top. So very straightforward setup. And as you can see that in the packing bed is where the reaction is taking place. That's where your H2S gas is typically getting oxidized. and you have clean air leaving the reactor. Okay. The other thing probably I did not talk about and why I kept it for here is, remember this, especially in wastewater treatment, because this was focused on wastewater treatment, most of the contaminants you are dealing with are somewhat polar in nature. Polar meaning they can dissolve in water or ionize in water. So I think most of you would know this, but Rebecca, do you understand what pH is? You must have learned this in school, that pH means how acid or how basic a fluid could be. So do you understand that concept a little bit?
Yeah, it's straightforward.
Okay, perfect. So when you have something known as an acid gas, right, that means acid is the low pH below 7, you can have more acid, right? And anything which is basic, the pH above 7 starts getting basic, right? Very basic concept. We have learned this in high school chemistry. And when you talk about H2S, it's an acid gas. And what does this mean? So this graph is trying to explain that to you, meaning that the lower the pH gets, the more gaseous H2S is. So at a higher pH, H2S would be ionized. But at a much lower pH, H2S is a complete gas. As a matter of fact, H2S is 98% gas when your pH is below 5. And at a pH of 9, your H2S is no longer a gas, it is completely ionized to sulfide ion, HS minus, as it is shown on your screen. Same thing goes with ammonia. If your pH is below 7, all of the ammonia in water or wastewater is going to exist as an ammonium ion. And the moment you go above a pH of 11.5, that is where, typically you have batteries and some other kind of fluids. Excuse me. Once the pH of your water is above 11.5, ammonia is a complete gas. That's why it's called a basic gas, and H2S is called an acid gas. So when we want to use chemical scrubbing, we want to make sure that all of your H2S is ionized. And that's why we raise the pH to roughly around 9.5, where your H2S is completely converted to a hydrogen sulfide ion, which is the first step, as you can see, because if you add sodium hydroxide or any kind of hydroxide, it is going to raise the pH of your water and wastewater. And then the next step is where we are injecting sodium hypochlorite. It is very commonly used as a disinfectant, but it's also a very good oxidant. And that's where you can convert your H2S to a salt. And you can essentially neutralize all your odors. I hope this is clear, because this is how chemical scrubbing works. Now, on the flip side, if you were dealing with ammonia, ammonia is a very basic gas, which means you need to lower the pH to about 7 or under. So you will use an acid, and then you will convert your ammonia gas into an ion, and then you will treat it. So you see, depending on the kind of gas you're trying to treat, if you're treating an acid gas, you need to create basic conditions within your reactor. If you're trying to treat a basic gas, you're trying to create acidic conditions in your reactor. There are multiple different kinds of chemical formulations. It depends on every company has their own trick and technique, but this is the very basis of chemical scrubbing. The last thing I want to cover here is the packing material. As I mentioned that you will always have some kind of a bed. In activated carbon, you will have an activated carbon bed. In chemical scrubbing, you have random packings, which are visible on your screen. If you guys have studied chemical engineering, you would know this. This is the subject most commonly covered in chemical engineering under mass transfer. But these packings, their purpose is multiple. the first thing they're doing is they are bringing the gas, which is your odorous airstream, which needs to be treated. And it is also making sure that the scrubbing liquid or the chemical which you're injecting for neutralization of the odors, they both are mixing. And the job of this packing is to create that turbulence. So this is, of course, not visible to the human eye because it's enclosed in a vessel or in a reactor, but the packing, what it's basically doing is it's increasing that surface area. So it is helping with that interaction, right? So if you go back to the slide, we were talking about empty bed contact time and bed velocity, right? The more empty bed contact time you have, the more packing or height of your bed will be, which basically means that you are going to get better mixing and better treatment and more neutralization of odors. Also, one of the other things what happens, which is not visible to the human eye, is the packing is what helps with creating those turbulent conditions inside and the mixing as well. So I don't want to get too much into fluid dynamics here, but if you guys remember, if a fluid is turning in different directions, its velocity goes up, right? Same concept applies here, but of course, this is happening at a microscopic scale, which is not visible to the human eye. So this is the heart of the process. Yes, you have the odorous air which needs to come in. Yes, you have the chemical which needs to come in, but it is really this packing which is helping with that interaction and that neutralization of odor. I hope everything is clear till here. We are just 3 more slides now. Rebecca, I know it's a little more scientific, but I hope you are enjoying this talk and are understanding at least at high level what odor control treatment looks like.
Yes, it's fascinating. I actually do have some background in water treatment, so surprisingly, this is just really interesting.
Okay.
Thanks.
All right. Thank you. Okay. The last step is biological treatment. This is very commonly used as well when you're dealing with high concentrations of H2S. This is by far the most economical technology when you're dealing with 100 ppm, 200, or even 1000 ppm of H2S, right? Now, it's a very simple thing. You need water here. And the reason is because microorganisms grow in the presence of water. You need moist conditions. It's a green technology, which means you won't be creating any byproducts, and mostly microorganisms are naturally present in the environment. So you are just enhancing them so they can neutralize odors. The most common bacteria you end up using is thiobacillus bacteria. This is called a sulfur oxidizing bacteria, and this is the only bacteria you typically require for neutralizing H2S. So most of these treatment technologies, as I mentioned to you earlier, have been focused towards H2S. Suppose if you had a lot of ammonia, you typically tend to use chemical scrubbing. And if you had VOCs, you may require activated carbon or some other kind of neutralization technology, which, again, if I had to cover all of this, it will take me a couple of days because there is a lot to this. And in this presentation, we just have to give you an overview. The good thing about biological treatment is, unlike chemical scrubbing, you won't be creating any harmful byproducts, because if you remember in the few slides above, in chemical scrubbing, I showed you that you are forming salt, right? Here, the good thing is you'll just be forming CO2 and water and nothing else. And you have a bed here, which basically, instead of just the random packing, which I showed you in the earlier slide for chemical scrubbing, is going to be made out of some organic material, which can help microorganisms grow on the surface of these beds where the oxidation and neutralization is happening. And yes, one of the things though, if your H2S concentration is very high, you can end up producing a lot of sulfuric acid. It is very acidic, which you will see in a couple of slides down. But this H2S, this sulfuric acid can have a value. You can either neutralize it, send it to your wastewater facility, or you can neutralize it with limestone, and you can discharge it. But H2S can be used in multiple places. Okay, so within biological treatment, you have 3 different types of equipment which can be used. One is called the biofilter. This is a very basic system designed for low H2S, VOC, and ammonia removal. Then you have biotrickling and bioscrubbers, which are typically designed for extremely high H2S concentrations. Now, I don't typically like to put a lot of wording on my slides, but I have used it here for you guys because this may be a new subject to you. However, this will become more clear when I show you the pictures of these units and everything. Simply put, what's happening here is you have odorous air, H2S, ammonia, VOCs. You have some oxygen. You may add some nutrients for proper biological growth, and microorganisms oxidize the odors and help produce water, salt, acid, and some sludge. As microorganisms grow, they tend to produce biomass, and that biomass is where the treatment is happening. But sometimes you need to clean it off as well because you don't want excessive growth. Okay, so the first one is a biofilter. This is basically what you see on your screen. One is a very large installation when you're dealing with extremely high flow rates. We are talking about 100,000 CFM. So it takes up a lot of space, sometimes even acres of land. And then you have some mini units as well. So it's a very simple setup. You have air coming in through a fan, and then you humidify this air. As I mentioned, for proper microbiological growth, you need moisture. And humidifier, what it's doing is it's adding that humidity or moisture to the air. So that way you can get the microorganisms to thrive. And then it enters into the filter bed. So again, bed velocity and empty bed contact time is very important, which is empty bed contact time typically is 30 to 60 seconds. And again, I'm going to stress on this thing. Empty bed contact time will also decide how much volume of your bed you will require, and your bed velocity will help with the even distribution of air. So both of those concepts are very relevant here and very important here because you want microorganisms to work. If you don't give them the right contact time, the microorganisms will not get their food and they'll die off. And then at the outlet, you are going to have odorous air, right? Then we have something known as a biotrickling filter. Very straightforward. You have water being just like a chemical scrubber. You have water being, introduced from the top. You atomize it, and then you have organic bed here. It could be made out of plastic media, or it could be made out of some kind of organic material which can promote microbiological growth. And then you have odorous air coming from the bottom. In biotrickling filters, water is very important. One, not only to keep the bed moist for microorganisms to thrive, but also, if you go back to the slide I talked to you about on H2S, you want to ionize your H2S as much as possible. And that is because once this H2S is ionized, it will get onto the surface of microorganisms, and that's where the oxidation is going to happen. So microorganisms, how they work is they need something ionized. So that can enter their body, they can use it, and then they can dispose of the end product, right? If you guys have dealt with microbiology, you guys would know this. Yes, Amit, you had something?
No, it was by mistake again, sorry.
Okay, all right. So as you can see, it's a very straightforward process. If you are dealing with high H2S concentrations, the bottom half of the bed is going to be very acidic because these bacteria, which I told you about, thiobacillus bacteria, they love thriving in acidic conditions for oxidation of H2S to sulfuric acid. So the bed at the bottom tends to be acidic, but as you're moving up, as the air is moving up and most of that H2S is getting treated, you will see that there is no more acid left. So you will get more neutral pH conditions because the pH of the water at the very top, which is being pumped in, is 7 to 9, right? And that's where most of your VOCs can be removed. So this is how simple this treatment is. And water is introduced only once. There is no recirculation here. So once the water is introduced, once the odors are neutralized, your clean air moves from the top, and then at the very bottom you have acidic liquid, which can be neutralized or it can be sent to your wastewater, because it's such a small volume of acid we are dealing with, it is not going to disturb the pH of your actual wastewater in the facility. And finally, we are dealing with bioscrubbers. Now, this is not so commonly employed in wastewater treatment because biotrickling filters are economical. With bioscrubbers, you need a larger footprint. However, if you're dealing with extremely high H2S concentrations, I'm talking about 5,000, 10,000 ppm of H2S, which is very common in biogas applications, that's where a bioscrubber could come into play. So it's very similar to what you saw in a biotrickling filter. Water is introduced from the top, it's atomized. You have odorous air at the bottom, and then you have a packing material. How it is distinct, though, is because now you have a mini bioreactor here. Now, if you guys have in school dealt with something known as an activated sludge, that is what really this bioreactor is. So you have all of this water, which is flown through the bed. It has ionized your H2S, and it is collected here. And then you have a bubbling reaction. You know, you just like in activated sludge, you introduce air to create a biomass and you to treat your water. Amit, you would probably know this because you must be dealing with nitrification, denitrification in reactors. So the same concept applies here for bioreactors, where you will be aerating this water, and the sludge will be your sulfur compound. So you will have yellow organic sulfur as sludge, which will settle at the bottom, and then you will have clean water, which can be recirculated back into this reactor. So in biotrickling filter, the water is only having one pass, meaning it enters the vessel, it treats whatever it has to do, then it is sent out, it is discharged. In this case, though, you don't want to waste water. You're treating that water again and recirculating it back. So majority, the work of a bioscrubber is two-stage. The first step within the main reactor is to make sure that those odors are captured. And then in the bioreactor is where most of these odors are actually getting oxidized or neutralized, but they're not getting released into the air because they're ionized in nature. Okay. And as you can see in on your screen, there is a basic setup of what a bioscrubber will look like. Yes, Amit.
So far, yeah, I think we have all of the system that you have mentioned.
Yeah.
I want to add a quick question. Sometimes, you know, like you have to continuously check the hardness of the water that is passing through the scrubbers.
Yes, that's correct.
Yeah, because you're consuming all those that smell, and you're treating it through that atomized water, and you see your hardness, like, you know, you'll see like the water is pretty hard. So in that case, you use some kind of salt to neutralize it. Sometimes in a day, you know, you consume like 100 kilograms of salt just for like a single scrubber. Can you tell me like what would be the reason for the scrubber that consumes a lot of salt just to neutralize the water, like the recirculation?
Yeah, so every site is different, and every source water, it comes down to the source water you're using, right? That's why,
Maybe
I mean, we
water for this one.
Yeah, feed water. I mean, we can talk separately. I can give you my phone number. We can talk about it a little more. It's much more complex than, you know, answering it here. It will take at least 10, 20, 30 minutes to answer this. So okay. I can explain you the science behind it, and we can speak about it separately. But just to put it simply, if you are using, if you have a lot of hardness, that is okay. But within the vessel, what happens is you can start scaling up your bed, and that can reduce your airflow. So you have to be very careful of that as well. I'll just stop at that for now, but it's a much bigger answer than that. So I need to understand the full context so I can answer that question better for you.
Okay.
Okay. Yes, Afrida.
Okay. Hadbhai, I have a question for you.
Yeah.
Suppose a municipal wastewater treatment plant has been getting complaints about a rotten egg smell, and your team collects air sample and runs through the technologies that you have mentioned, but received low levels of hydrogen sulfide.
Yeah.
Okay, that is basically below the lab's ordered threshold level, but you are getting still complaints from the residents.
Yeah.
So my question is, have you run into this kinds of situation where the technologies didn't capture the odor compound? And if yes, how was that gap handled?
Yeah, good question. So I was actually going to show that to you guys in a case study. We are done here with the presentation. Okay. And I am going to show you the next slides, which I had in mind for this. So that question actually goes directly to one of my first sites when I started in odor control. So let me just open that slide for you guys. Okay. All right. Let me just present here. Window. All right. You guys see my screen?
Yes.
Yeah, okay, good. So what happened was, I'm talking about 2019. I had to do my first commissioning on a site in York region, and I don't want to take names here, but the system was designed for H2S removal. Okay, and that's what the municipal spec called for, and we ended up doing this whole system design for H2S treatment because people were confident that there is H2S, and that's why you need to spend $300,000 to have an H2S removal system. Okay, we installed the system, and smells are still coming. The odors are still, the neighbors are still complaining, the municipality is still complaining, and they came back to us that, hey, your system is not removing H2S. And I was like, that's not possible. So we did a full thorough analysis. When we did handheld portable analysis, we got H2S measurement as 0. So, and when we went to site, we did notice that yes, there are smells. There is some distinct smell, but it is not H2S because I had enough experience with H2S smell back then. But yes, it was smell, and people were saying, no, it is still H2S and your system is not designed properly. So we did a complete air analysis. We sent it to the lab to see what is in this air to get a complete breakdown, because portable units can just measure certain gases. And for VOCs, they just tell you the total, but they don't tell you exactly which VOC is responsible for a concentration, right? So what you see on your screen is reduced sulfur compounds, which is H2S and any organic sulfurs. So when we did the test, you will notice that there is a detection limit set by lab for the GCMS, gas chromatography mass spectrometry. And you see here that everything is non-detect. And we did this a couple of times. I'm just showing you one example, but we did this a couple of times and we figured out that there has never been any H2S. So this whole system design from the very start was wrong. When we moved to aldehydes, okay, that's when we got to know that, okay, you know what, the entire system design was wrong, but what is causing this odor? There is a smell, but it's definitely not H2S. And once we started looking into it, we found out there is formaldehyde, there is acetaldehyde, and there is methyl ethyl ketone, which are also very common forms of odors. I know I said VOC as a big word, but many of the times it is going to be either aldehydes, ketones, or alcohols, which are going to give you these kind of smells. So this was the aldehyde and ketone test, which was able to help us determine that, okay, there never existed any H2S in this place. It was always VOCs. We did another test just to look at VOCs, and this is another of these tests. And to answer your question, I know, Amit, you had asked whether VTEX is available or not. You can see every VOC which was there. We had a little bit of propylene. We had a little bit of carbon disulfide, again, a side reaction. This is again created from H2S, very common. We had methyl ethyl ketone, which was confirmed again. But the more we went down, we noticed that we had some benzene also. So luckily, what happened was our system was working on a few things, but our system was originally designed for H2S. It was never designed for these compounds. So once we changed the configuration of our system and we included activated carbon system or a media which could remove these kind of VOCs, we were suddenly getting to non-detect. So as you can see here clearly, this is the inlet air, this is the outlet air, and this is the radial detection limit. This is where typically labs have their equipment, and this is the minimum concentration they need for detecting something, right? So you can see that suddenly a system which was designed for H2S had many different kinds of odors from different compounds, not related to not related to H2S. So Amit, you had asked about BTEX. This site specifically had benzene. This site had styrene. All of these which are very common from industrial sites. And this is what a typical lab analysis will show you, each individual compound, what is the inlet concentration and what is the outlet concentration if you have a treatment equipment in place.
Okay.
I hope, Afrida, this answers your question.
Perfect. Thank you.
Yeah. The last thing I quickly wanted to touch on, guys, I know it's we are well ahead of above time now today, but I just wanted to show you the importance of data and from a treatment perspective. So I did a small pilot in California a couple of years. I'm talking about 2022, and this was using a portable handheld equipment. So as you can see, this testing was done from 31st of January to about 11th of February, so just about 2 weeks. And this is what a handheld analyzer does. It gives you the H2S concentration, which is in blue. It gives you also the temperature of that odorous airstream, which was being measured in green. And then it also tells you the relative humidity. So this was actually for a lift station. For those of you who don't know what a lift station is, it's basically a pumping station. It's a big pump which pumps wastewater from low elevation to high elevation. That's why it's called a lift station. Amit would actually, of course, know this already because he's working in wastewater plants. But you see here that the average. Yes, Amit.
Quick question, Hayat. So, regardless all those odor creating gases, have you guys consider measuring the greenhouse gases also from this one? I know it's completely out of the topic, but
no, we should actually. I personally agree with you, but I think there is only one sensor to date. The most common greenhouse gas you have to look at is methane, number one, which you can measure for. But the most important one these days is nitrous oxide, N2O.
that's
And
true. But both of the gases, you cannot smell them, right?
You cannot smell them. You will need an analyzer.
That's true. And because I'm with the Professor Al Said. I'm helping on their project, and it is also part of my thesis report. I've been looking at the 17 different sensors in Bonnie Brook, Calgary.
Yes.
So all those sensors. My other question, because I when you show me those types of smell like benzene, sometimes if you go to the aeration tank, I smell like good smell. It's not a bad smell, but I smell like it's okay. I smell like a soapy kind of things, right? In those tanks.
Yeah.
Now, when I saw, okay, it could be a benzene or toluene. Now I'm worried because I might be smelling those kind of chemicals over there. Do you guys also have something that does online analyzer on the site? For example, just by the aeration tank or by the final tank.
Yeah, you can have. Multi-ray is a very good one to consider. This is Acrolog, what you see on your screen, but there is a thing called Honeywell Multi-Ray, MULTIRAE. That's the company you can use. It's a very good handheld instrument, but you have to understand this, even in the analyzer world, they can give you only total VOCs. They cannot tell you exactly which VOC it is. You will have to send that air sample to the lab to exactly know the breakdown of each compound.
Okay.
Yeah. But yeah, no, I actually like that point because for those of you who did not know this, nitrous oxide has 300 times more potential than methane or CO2. I believe CO2.
Yeah, CO2. Yeah, the
Yeah,
carbon
CO2 for causing global warming. So as much as we have always focused on methane and CO2, it is really nitrous oxide from wastewater treatment facilities, which is a big contributor to GHG emissions. And there is unfortunately not a good way to neutralize it. A lot of people are looking at anaerobic treatment like Anamox as one way, but nitrous oxide is unfortunately a byproduct of nitrification in wastewater treatment. And I think, Amit, you could speak more to it. My only background in wastewater is odor control, but the more I have been reading, wastewater alone is responsible for 2 to 5% of the total greenhouse gas emission globally.
Yeah, that's true. I think that's the number according to the IPCC. But yeah, they say okay, it's normally the wastewater treatment plant are 5% responsible for the.
Yeah, I mean, we have a small system which can treat like ppb level concentrations, but ppm level concentrations, unfortunately, there is no good technology yet.
Oh, okay.
Yeah, so you will have to use something like a thermal oxidizer, which typically used in oil and gas industry, but then they use a lot of fuel. You need methane again. So this is the irony with some of these treatment technologies, right? You need fuel, which will have a carbon footprint to neutralize something which will have a bigger carbon footprint.
Okay.
Yeah. So data is very important. Just this is the last thing, guys. A few more minutes. I'm really sorry it took a little longer than expected, but you see, we did a pilot, and this was the inlet concentration. And typically, whenever you get into odor control for wastewater treatment facilities, you have something known as a performance testing to show that your equipment is capable of treating the odors. Okay. Now, this is just a full spectrum, but if I shorten this, if I wanted to see for a specific day, I can vary the concentration around. And then at that specific point, if I wanted to see a peak, it is telling me that it was 16 ppm and my humidity was 76%, and my temperature was 60. So in winter months also, California has pleasant winters. So you can still have a lot of odor creating potential, right? Now, moving back to the full timeline, it gives me a very good idea. If I remove the H2S, for example, it is telling me where my temperature was. So pretty much the temperature was pretty much 15 degrees Celsius throughout in this area. So still pleasant weather, which is enough for producing odors. You typically start producing odors when your wastewater temperature is over 10. More significantly, below water temperature of less than 10, you don't produce that much odors. You could still, but more above 10 degrees Celsius. So this tells me that odor was being produced and this was the temperature, still a very good condition for microorganisms, but humidity was also there. So this also tells me, because this system was designed for removal of H2S, because of the amount of humidity present, there could be a lot of H2S in liquid form as well. So as I mentioned to you guys, that H2S can ionize itself depending on the pH of the water. And in most cases, wastewater has a pH in the range of 6 to 8. So if I'm getting such a high H2S concentration in gaseous form, I can hardly imagine how much it would be in liquid form. And these peaks kind of tell me that either there is a lot of microbiological activity happening, or no one ever thought of even treating the sewer water. And that's why you end up creating so many odors in that sewer. So our goal was, of course, to make sure that the neighbors are not giving any odor complaints, and that's why we had equipment installed on this lift station to make sure that none of this H2S is escaping. Okay, but this is what a typical graph would look like when you're doing a pilot or any air analysis for how many ever days to get a good data. Because without data, just like anything you do, you will not be able to design an effective treatment system. Okay. So this was the background, and just the final slide I wanted to show you was the output. What happened when this odor passed through the activated carbon system? So what you see on your screen is pretty much all of the H2S was neutralized, except that there was a minor spike here, you see. But again, after that, the system was running just fine, and we got our odors down to almost zero, specifically H2S. The temperature varied a little bit. Now, if I just go to the temperature graph, you see here that the temperature did rise up a little bit. Now, activated carbon process, for those of you who do not know, it's an adsorption reaction. So in any adsorption reaction, regardless of activated carbon or whatever you use, does increase the temperature a little bit. These reactions are exothermic reactions. So that's why you see that the outlet air, the temperature had increased significantly. But humidity, on the other hand, was also fluctuating. You saw initially that we had a very good curve and the humidity was in the 80 to 90 range continuously. But here, this is telling me that some of that humidity got trapped in the activated carbon bed. And that is why it was fluctuating so much, okay? And that can explain why my H2S, I had a slight spike here. Like if I just focus on going to this timeline after 10 days, this tells me that there were some conditions which happened. Either there was maybe excessive H2S formation, or there could have been maybe unaffected, like there was not enough aeration, or because there was excessive moisture in the carbon bed, that some of that H2S probably never reached the pores of the activated carbon bed or carbon material, and they got released. So there was that minor spike. Luckily, 0.6 is not so bad. It's 60 ppb, still where humans can smell it. But by the time it goes into the atmosphere, it will get neutralized. So it may have not, there would not have been any odor complaint. But once that situation was resolved, you see that the system was performing again and completely neutralizing the odors. So this is just a high-level representation of why data is important. And you can see when I move back how this peak happened, but the peak is at 0.6, right? So this is why data is very important, not only from a standpoint of what is causing the odor, but also for understanding how well your equipment is running and why sometimes optimization of your equipment may be necessary, okay? With this, I think I have spoken enough for about 2 hours today. I'm tired now, and I would like to take any final questions before we we close this session today.
Yeah, that was good presentation, Hayat. Got to know lots of things.
Yeah, I know there's a lot we had to cover today, and I took a little longer than expected, but this is, I mean, hopefully now for someone like Rebecca, I know we were speaking about this at the start of the call, but now you can understand the importance of odor control and why it is so crucial, right?
Mm-hmm.
Yes, absolutely. Thanks.
Yeah, and Afrida, Hajira, you guys have any comments or any things you wanted to share with me about your experience today?
I wish we have more audience for this session, because this session is so much informative and engaging. Thank you so much.
Okay. Hajira, you have anything? I think she is not there. Well, thank you guys so much. What we will do, Afrida, is we will make these slides available to everyone, whoever attended, and I will put in my contact information as well. So if you guys want to reach out with more questions and you want to learn a little more or you want to get more resources on this topic, I'll be more than happy to share that with you guys. And it's a fun topic. I hope to continue in this area of practice for at least however long I can. So I'll be more than happy to assist you guys. So thank you so much for listening in today. I hope I was as clear as possible.
Quick question, Hyde. Are you sharing this slide through the college, or there's some?
I think I have been asked to share with the college, so you will have to ask the college about it because I'm presenting on their behalf. But what I can do here in the chat quickly, I can just put in my phone number and email address, so you guys can contact me anytime you need for anything else on this.